This section on L'Hopital's rule shows a new way to take limits. What I'm going to do is write up the theorem and then do a bunch of examples. Then we'll talk about the theory after I've done some numerical examples. So here's the rule, L'Hopital's rule. It looks like this. Suppose f and g are differentiable in an open interval I, and suppose that A is some number in that interval. Now, if g prime of x does not equal 0 when x does not equal a, on I, and if the limit as x goes to a, f of x, equals the limit as x goes to a, g of x, all of those limits equal 0, then the limit as x goes to a, f of x over g of x equals the limit as x goes to a, f prime of x over g prime of x, assuming that last limit exists. The rule also applies to x going to plus and minus infinity, x going to a plus, x going to a minus. All those types of things are included in this process. So what I'm going to do are a bunch of examples. I'll start with the most straightforward one I can at first, show you how this works. The idea is this. You're confronted with a limit that comes up to the form 0 over 0. We see them all the time, and we've always had to do some sort of algebraic thing to cancel out the stuff that was 0. Well, this is going to let you bypass that by taking derivatives. So I'm also, when I do each of these examples, I'm going to tell you about something called an indeterminate form. This one will have the indeterminate form of 0 over 0. What that means is that when you try to plug in the numbers, you'll get a 0 over 0 type of an expression, and from that you're not able to determine a numerical value. We don't know what it is until we do more work. So here's the example. The limit as x goes to -1, x to the 4th plus x cubed plus 2x plus 2 all over x plus 1. Now you can see that the denominator is going to be 0, no problems there, but let me check the numerator. So the first thing I'll try to do, like any other limit, is I'll just try to plug in the target value and see what happens. So I'll have -1 to the 4th plus -1 cubed minus 2 plus 2, and that'll be over -1 plus 1, which is 0 over 0. So since this is 0 over 0, I may apply L'Hopital's rule. So what I'll do, I like the way a book did this once before, and I'm going to use that myself. They put a little L with a circle around it to indicate when L'Hopital's rule had been invoked. So that means I'm going to take the derivative of the numerator. I'll get 4x cubed plus 3x squared plus 2 all over 1. The derivative of x plus 1 is 1. And now I'll see if I can just plug the numbers in as before. So I'll see 4 times negative 1 cubed plus 3 times negative 1 squared plus 2. That's going to be negative 4 plus 3 will be negative 1 plus 2. That will equal 1. Now I encourage you, when any of these are done, to go on your calculator and graph it to see if you get the same results that are here. Because sometimes you'll have to do some pretty hairy algebraic manipulation to make things work. Here's another one with the same form. The limit as x goes to 1 for tan inverse x minus pi all over x minus 1. And so if I tried to plug in 1 directly, I would see 4. Tan inverse of 1 is pi over 4, so I'd have 4 times pi over 4 minus pi all over 1 minus 1. Well, this will be pi minus pi over 1 minus 1. So once again, that's a 0 over 0 situation. I may invoke L'Hopital's rule. The derivative of inverse tan is 1 over 1 plus x squared. So in the numerator, you're going to get 4 divided by 1 plus x squared. The pi, when you take its derivative, just goes away. And of course, in the denominator, the derivative is 1. Now, I'm going to see if I can just plug in 1. This 1 down here doesn't mean anything. If I plug in 1, I'm going to get 4 over 1 plus 1 squared, and that will equal 2. Let's try another example. The limit as y goes to 2, y squared plus y minus 6 divided by the square root of 8 minus y squared minus y. So you remember this. Let me plug in the 2 in the numerator and see what and the denominator and see what happens. In the numerator, I'll get 2 squared plus 2 minus 6, and in the denominator, I'll get 8 minus 2 squared minus 2. All right, so I get 4, 6. I'll get a 0 in the numerator. And in the denominator, I'll get 8 minus 4, but the square root of 4 is 2, so 2 minus 2 will be 0 over 0. Now, in previous problems, we would have expected you to do this, but I would have had another polynomial underneath of it so that you could perhaps factor things and make them work. But this does not look pleasant to try to do anything with down here. So L'Hopital's rule is really helpful in this situation. The only thing, though, is your algebraic capabilities are going to be stressed. If you're not good at algebra, this is a great time to practice, because stuff like this being in denominators and things like that is nothing but trouble. All right, the derivative of the numerator is 2y plus 1. The derivative of the denominator, well, the derivative of square root is 1 over 2 times the square root 8 minus y squared. But then you have to apply the chain rule and take the derivative of what's inside. That'll be negative 2y. And down here you'll get minus 1. Now, I'm going to see after doing this, I don't want to do anything else. I just want to see if I can plug the 2 in. If I plug the 2 in up here, I'll get a 5. If I plug the 2 in down here, that'll be a 4. And that'll be a negative 4. Those will cancel, but I will not get 0 over 0. So let's just plug them in right now. I have 2 times 2 plus 1 all over negative 2 times 2 all over the square root of 8 minus 2 squared. Oh, I had a 2 down there also. I took this negative 2y and simply put it on top of this little fraction here. Let me increase that. So I'll get a 5 here. I'll have -4. And it'll be 8 minus 4 will be 4, but the square root of 4 is 2, and 2 times 2 is 4. And this will equal 5 over -2. And there you go. The next indeterminate form is infinity over infinity. And of course, L'Hopital's rule says it works for infinity over infinity. So let's do some examples involving this. So we'll do the limit as x goes to infinity. 4x cubed minus 2x squared plus 6. And in the denominator, we have pi x cubed plus 4. Now you may remember when you're dealing with a rational function, if the powers of the numerator and denominator have the highest powers are equal, then you simply have to take the quotient of the leading coefficient. So the answer to this will be 4 over pi. However, let me go through the L'Hopital's rule just to show you that that works. You should know that any polynomial goes to infinity if it starts off with a positive coefficient. So both of these are going to infinity. That works for any power, any infinity. The only thing that it wouldn't work for is a horizontal line. But other than that, these are always going to be going infinity over infinity. So there's our indeterminate form. And I'll go ahead and apply L'Hopital's rule. So I'll get 12x squared minus 4x in the numerator. The denominator, I will get 3 pi x squared. Now I still have a polynomial over a polynomial, and it's still of the form infinity over infinity. So I can apply L'Hopital again. I keep going until I run out, until I get to a place where I can plug things in. But as long as it's in the indeterminate form, I'm going to keep plugging away. So this will be 24x minus 4 all over 6 pi x. And it's still a polynomial over a polynomial, so it's still infinity over infinity. And I'll keep doing L'Hopital. Uh, 24. The numerator will be 24, and the denominator will be 6 pi. And from here, you don't have to do anything except simplify, because this will equal 24 over 6 pi, which is 4 over pi. How about the limit as x goes to infinity? Natural log of 3x plus 5e to the x divided by the natural log of 7x plus 3e to the 2x. Now you ought to know, in an earlier video, I don't know how long ago, but if the inside goes to infinity, then the natural log of something going to infinity is still infinity. So this is still going to be infinity over infinity. So the first thing I will do is L'Hopital's rule. Take the derivative. The derivative of this up here, remember you've got to do 1 over whatever's inside. So I'm going to have 1 over 3x plus 5e to the x. But then I got to take the derivative of what's inside. And I'll get 3 plus 5e to the x. The denominator works in a similar fashion. I got to first take 1 over this stuff, so I'll get 1 over 7x plus 3e to the 2x times 7 plus, this is a little more complicated because of that 2. When you take the derivative, it'll be 3e to the 2x, but then when you take the derivative of 2x, you're going to get an extra 2. So you get 6e to the 2x. Now, can I possibly plug in infinity? Well, that's kind of hard to do. It's really complicated right now. I think what my best bet now is perhaps to write it as a simple fraction, because this up here is a fraction and this down here is a fraction. So let me clean up a little bit before I do any kind of L'Hopital. So I'm going to get 3 plus 5e to the x over 3x plus 5e to the x times, now that this will be in the numerator when I flip this fraction here, so I'll get 7x plus 3e to the 2x divided by 7 plus 6e to the 2x. Now, it's possible that you might want to multiply it all out, and there's nothing wrong with it. It just gets ugly and it gets complicated. One of the things that you can do with limits, assuming that all of these limits exist, is I can break this up in the following format. Assuming both of these limits exist, I can break it up as a product of limits like that. Now, e most definitely goes to infinity, so this is an infinity over an infinity. Same thing over here, an infinity over infinity. So let me write that down. I have infinity over infinity times infinity over infinity. So I'm going to do a L'Hopital on each one of these. So I'll do a L'Hopital on the first limit. As long as each of these limits exist, I'm fine. All right, when I take the derivative here, I'm just going to get 5e to the x. And then when I take the derivative down here, I'm going to get 3 plus 5e to the x. Some of you at this point might say, well, this is obviously going to be 1. And you're right. I mean, if you get to the point where you can tell what the limit is without taking another step, all the better. I'm going to do the same thing on the second one. I'll get 7 plus 6e to the 2x all over 12e to the 2x. Now I still have infinity over infinity, infinity over infinity. Because of those e's, the e's will force that. So I'm going to do L'Hopitals again. Five e to the x is 5e to the x. The derivative of that is 5e to the x. The derivative down here is 5e to the x. Here I'm going to get 12e to the 2x divided by 24e to the 2x. Well, this is nice because you just cancel these. That's going to be 1. Here I can cancel the e to the 2x's, and it looks like I am just left with 1/2. 1 times 1/2 will simply be 1/2. Next, indeterminate form. Students may be tempted when they see something like 0 times infinity to write 0 or infinity. I'm not sure exactly which one that they might think. Probably more along the lines of 0, because 0 seems to wipe out anything. You cannot do that. There is nothing here that indicates that this is going to be 0 or infinity. In fact, look at some of our examples and you'll see that they turn out to be something different. So for our first example, let's take a look at the limit. As x goes to 1 from the left, 1 minus x times tangent of pi over 2x. And just to remind you what tangent looks like when it gets near to pi over 2 but to the left of it. Tangent comes like this. I don't want to draw too much, but basically it has a vertical asymptote and it's going to positive infinity. So if x is a little bit less than 1, then this is a little bit less than pi over 2, which means that it's tending towards positive infinity. Of course, if you plug x equal 1 into this part, you're going to get 0. So we do have a 0 times infinity situation. L'Hopital's rule is not meant to handle anything like this, but we can manipulate the problem so that it follows a L'Hopital situation. I'll show you what I mean. There's more than one way to do these. I'm not doing any L'Hopital just yet. I'm just rewriting. I'm going to leave the numerator as 1 minus x. You're like, what numerator? Well, I'm making a numerator now. 1 over tangent is cotangent. Now, if I try to plug in x equal to 1, I'll get a 0 in the numerator. If I try to plug in x equal to 1 in the denominator, cotangent of pi over 2 is cosine of pi over 2 divided by sine of pi over 2. That's 0 over 1. So I'll get 0 over 0. That's the format it's in. Now I'm allowed to apply L'Hopital's rule. The numerator is easy. That'll be negative 1. The denominator, the derivative cotangent is negative cosecant squared. But then don't forget that when you take the derivative, you have to take the derivative of the stuff inside, which in this case will be pi over 2. All right, it might be difficult for you to see with all these things going on, negatives and things like that. I'm going to simplify this somewhat and try to write it in a form that you can see without much difficulty. First of all, these negatives can cancel. Second of all, I can rewrite cosecant squared down here as sine squared in the numerator. And then finally, I can reciprocate the pi over 2, so I can have 2 sine all over pi. And now let's see if I can plug in 1. If I take and plug in x equal 1, I'm going to get sine squared of pi over 2, and that's equal to 1. So 2 times 1 squared over pi will equal 2 over pi. This one, the limit as x goes to 0 from the positive side, sine of x times 1 minus x over x, the square root of all that. So let's see what happens if I try to plug in x equal to 0. Well, I get sine of 0 is 0, that's for sure. But here, I'll get a 1 in the numerator inside the radical, but down here, that thing is going to 0 from the right-hand side. So this will be 1 minus, that'll be a positive number in the numerator. This is going to 0 from the positive side. So this piece is going to positive infinity. Well, the square root of it is therefore going to positive infinity. So I have a 0 times infinity format. Now, there's a number of ways to make this work. I thought about like taking and dividing, like changing this to 1 over cosecant, but then its derivative is cosecant cotangent. It seems like it gets kind of ugly, because then if I have to do successive derivatives, the secant cosecant is going to break up into more of a colossal pain. So instead, I'm going to rewrite this. You'll come up with your own thing that is comfortable, but when you're first doing a little experimentation might be in order. I'm going to rewrite this as sine of x divided by the square root of x divided by 1 minus x. Did you see what I did there? I put it in the denominator, but I flipped inside, so I still have the same thing as I did before. Now, if I try to plug in 0 for x, I'll get sine of 0, which is 0. If I plug in 0 down here, I'll get 0 over 1, which is 0. So I can apply L'Hopital's rule. Now, I know you're looking at this and going, this is not going to be pleasant. And you're right, it's not going to be, but that's what I was talking about when it comes to some of the algebra. You're going to have to be on your toes and you're going to have to take your time. All right, the derivative of sine of x is cosine of x. Now, this also, to me, is good news because when I plug 0 into cosine of x, that's going to be cosine of 0 is 1, which means that this should be the last step in my L'Hopital because I got a non-zero or non-infinity thing up there. It may not be, but it should be. So let's see what we have here. For the square root, the first thing you do is do 1 divided by 2 square root x over 1 minus x. And then you need to multiply by the derivative of the stuff inside. So I'm going to use the quotient rule on this stuff. Remember how that goes. Take the derivative of the numerator, 1 times 1 minus x, minus, now leave the numerator alone, x, and take the derivative of the denominator, divided by 1 minus x squared. Now, as you can imagine, there's a great deal of simplifying to be done before I'm going to get any answer. Is that necessarily true? Let me just see for a second what happens. If I try to plug in 0, I'm going to get a 0 in a denominator right here. So I'm going to stop right there and let me do some simplifying before I do anything more. Let me keep this here for a minute. Well, actually, I think what I'll do is rewrite this piece as 2 times the square root of 1 minus x over x. Notice how it flipped there, because it flipped. I moved it up a step from there. Times, here I'm going to get 1 minus x plus x. Now, I have a fractions over fractions, so I'm going to rewrite this just a little bit more. Cosine of x will stay where it is. But notice this here can flip again. And this can too. And all of that is over 2. Well, let me try to plug it in. If I plug in 0, I'll get a 1 there. This part will be 0, and this part will be 1. I get a number. I'm good. So I'll put those in there. I got cosine of 0 times the square root of 0 over 1 minus a 0 times 1 minus a 0 squared all over 2. And I'll leave it to you to check the details. This answer turns out to be 0 to infinity. To the limit, as x goes to 0, 1 plus 4x to the 3 over x. This is sort of a complication. I probably should have put a plus on here, but let's see what happens as we do it. If x is going to 0, this piece right here is going to 1. And if x is going to 0, well, this is either going to infinity or negative infinity. Let me go ahead and put a plus here because I think there it needs it. This way I'm ensured that this is going to go to positive infinity. So I'm on the format 1 to infinity. These are really kind of interesting. What you do in these is probably not what you think. Here's what we do. Do you remember, I could take any number, let me call it theta, and rewrite it as, well, as long as theta is greater than 0, I could write it as e to the ln theta. Right? So that's precisely what I'm going to do here. I'm going to rewrite this as the limit as x goes to 0 from the plus of e to the ln 1 plus 4x to the 3 over x. Now, there's complications in what we're doing right here. The fact is, you have a limit on the outside of all this, but yet I've rewritten just this portion of it. What do we do here about that? Well, you've got to remember that e to some power, e to the x is a continuous function. So what that means is if you have the limit as x goes to a, e to the x, that equals e to the a. That means basically I can take the limit and put it up in the exponent. So this equals, I'm going to draw a giant E here, and we'll do something about this horrible looking E in a minute. But for right now, just follow what I'm doing. All right, as you can see, there is a lot of stuff going on in the exponent. So a convention has been developed to handle massive exponent at E problems. And what we do is instead of this big E, we simply write exp, and in brackets, I put the exponent. Okay, so just keep this in mind. exp, when you see exp of x, that's just e to the x. All right, well, the beautiful thing about this is, first of all, this thing just kind of hangs around till the end of the problem. And watch what happens inside of the brackets. I'm going to take this 3 over x and bring it out front. Now, in the future, I'll do this a lot faster than I am right now, but I want you to see each and every step. What I'm going to do here is rewrite this as, and this should have been gone. That's gone once I put it in the front like that. I'm going to rewrite this part of it as 3 ln 1 plus 4x divided by x. Now, look at just the fraction. If I plug 0 in for x, I will have 3 ln of 1. ln of 1 is 0. If I plug 0 in for x, I'll have 0 down here too. So I will have a 0 over 0 limit. Now I can work just inside the brackets and do L'Hopital's rule. Don't forget the CXP. Just keep writing it, because you'll forget it if you don't. All right, let me go ahead and take the derivative of the numerator. The 3 won't be affected, but this part, the ln of 1 plus 4 over x will be 1 over 1 plus 4x. But then you also need to take the derivative of 1 plus 4x, which is 4. The derivative of x couldn't be easier. It's just 1. And at this stage, I would see if I can just plug the x equals 0 in. So I'm going to have 3 times that times 4. I'm going to put that as 12 over 1 plus 4 times 0. So that equals exp 12, which is e to the 12th power. And you can see the original indeterminate form was 1 to the infinity, so it didn't come out to be 1, it didn't come out to be infinity, it came out to be e to the 12. And I think this one sort of has the same deal about it too. Whether this is plus or minus infinity will make a difference. So I'm going to put a plus here like I did before. And that way that just says that this is going to plus infinity. Here, if you plug in 0, you'll get 2 to the 0, which is 1. Plus 0, you'll get... So this is a 1 to infinity type of a problem. And exactly the same thing is going to happen before. I'll just jump right to it. You're going to get to exp, bracket, lim, as x goes to 0 from the positive, ln 2 to the ax plus x divided by x. And you can see I did it all in one swap. I brought the 1 over x down, but the 1 doesn't do anything. I'll just put the x in the denominator. And now let's see what we have. If you plug in 0 for x, this part in here will be 1. ln of 1 is 0. And you'll get 0. By the way, I don't think I mentioned, a is just a constant. Let's just, a is a constant. I just don't know what this value is. So we'll go ahead and do L'Hopital's rule. And the same deal has happened as before. I'm going to get 1 over 2 to the ax plus x, and then the derivative of the stuff inside. Do you remember the derivative of 2 to a power is immediately 2 to that same power times ln 2. But then we've got to take the derivative of ax, and that'll be a. And the derivative of x is 1. And all of that is over 1. And now let's see if I can plug in my 0. If I plug in 0 for x, I'll get 1 over 2 to the 0. I'll get 1 over 1. That won't be a big deal. It looks like I'm not going to have a problem with plugging in. Let's go ahead and do it. exp. So I'm at 1 over 2 to the 0 plus 0 times. Notice this divided by 1 just disappears. It's not to be taken into account. So we have 2 to the 0 ln 2 times a plus 1. That equals exp. So this part here is just 1, so that has no bearing on anything. It looks like I'm going to have ln 2 times a, which if you don't mind, I'm going to write it as a ln 2 plus 1. And I guess you can keep it like that. There are other things you can do, but I'm not going to require that. This you can rewrite. The final answer is e to the a ln 2 plus 1. I mean, there are other things that you could do. For example, you check this out on your own. You can rewrite this as 2 to the a times e. Maybe you like that one better. This is just a matter of taking that a, putting it up there, noticing that e and ln cancel, and then e to the 1 is e. So whatever one you like better. Neither one will be required. Indeterminate form. Zero to the 0. Here we have limit x goes to 0 from the positive side, x to the 4 over x. Whenever you do this, the reason I put the positive here is because if you try to approach 0 from the left side, you'll be taking negative numbers to very strange, maybe even irrational exponents, and you'll have non-real numbers. We have all real numbers as long as I stay in the positive realm. So 0 to the 0, this is certainly a 0 to the 0 form. You're going to do exactly what I did before. And you're going to rewrite this as exp lim. x goes to 0 from the positive. Now this time what you're going to do is ln x to the 4x. It's a little bit different than what we did before. I'm going to still bring down that 4x. Except now it's not quite so simple. I can't plug in the 0 from the positive because this will be an infinity. I'll have a 0 times an infinity. That's still an indeterminate format. But what I can do is this. I can rewrite this fraction as 4 ln of x divided by x to the negative 1. You see here then, if I plug in 0 from the positive side, this top will become a negative infinity. If I plug in 0 from the positive side down here, this will become a positive infinity. So my form is a L'Hopital's form. You're allowed to have a mixture of infinities in there. So now I'll apply a L'Hopital's rule. Take the derivative of ln x and you get 1 over x. Take the derivative of this and you get negative x to the negative 2. And at this stage I want to do a little simplifying. 4 over x divided by negative 1 over x squared. I'm just rewriting this as negative 1 over x squared. So I'll flip that fraction. I'll take out an x, and it looks like I'm left with just negative 4x. So this will be exp lim, as x goes to 0 from the positive side, negative 4x. You just plug in 0. So this equals exp of 0, which is e to the 0, which is just 1. So did this one actually 0 to the 0? I think some people believe that should be 1. So for those few people, this is a case where that worked out. What do we have? Infinity to the 0. I don't know what you think that might possibly be, but whatever you think it is, it may or may not be that. You might be thinking that it's 1, and in some cases that does happen that way. Here I'm going to do an example that is similar to the one I did before. The limit as x goes to, this time infinity, 1 plus 4x to the 3 over x. So if you try to do the infinity here, this part will become 0. 3 over infinity will be 0. But this part in here will be infinity. So you'll have an infinity to the 0 situation. So I'll do exactly what I did before. I'm going to rewrite it as exp limit as x goes to infinity, 3 ln 1 plus 4x over x. And you're going to see we're going to go through exactly the same steps that we did before. You're going to have ln infinity is still an infinity over an infinity. So now I'm permitted to use a L'Hopital's rule. And as before, I'm going to have 3 times 1 over 1 plus 4x times 4, and in the denominator I'll have a 1. Well, this is a really simple one. I'll go ahead and rewrite it so that it's evident, but I'll get 12 over 1 plus 4x. And in case you should know this by now, that if you only have a variable in the denominator which is going to infinity, then the whole thing goes to 0. So this equals e to the 0, which equals 1. Is infinity minus infinity. Students are dying to put infinity minus infinity equals 0, but as with anything else, you cannot trust that. So let's do it as an example. The limit as x goes to infinity, x minus the square root of x squared plus 1. In a form like this, many times you can avoid L'Hopital's rule, but you have to typically do a trick to get this into a fraction format. The trick is this. I'm going to write this as over 1, and then what I'm going to do is multiply by the conjugate. We saw this in some tricks that we were doing before, but we didn't end up doing L'Hopital's rule. We played around with exponents and things like that. Well, the numerator is easy because it's a difference of squares formula. So you're going to have this squared, x squared minus this quantity squared. Now, in the numerator, the x's go away completely. And we have negative 1 divided by x plus the square root of x plus 1. Now, you may want to apply L'Hopital's rule. However, the problem with this numerator is it's not 0 or infinity, even though this denominator is infinity. You must recognize that any number over infinity equals 0. Couple of notes. The limit as x goes to infinity, x to the n over e to the x always equals 0. The reason why is because if you apply L'Hopital's rule, you can see this will be infinity over infinity. You apply L'Hopital's rule and you'll get something like this. Nx to the n minus 1 all over e to the x. e to the x stands the same each time. This is still going to be an infinity over infinity unless I've zeroed out the exponent. So I can do it again. N times n minus 1, x to the n minus 2 over e to the x. And I can keep doing this until I've exhausted the n's. In fact, you can keep going until you arrive at this expression. Once you've taken out all the n's, you'll end up with n factorial in the numerator. The denominator will still be e to the x. Well, here you have a number divided by something going to infinity, so this equals 0. No matter what is. So in particular, if p of x is a polynomial, then the limit as x goes to infinity, p of x over e to the x equals 0. Without stretching the imagination too much, you should also be able to see that if I try to do e to the x over x to the n, that will equal infinity. Similarly, the limit as x goes to infinity, x to the n over ln of x equals infinity, and the limit as x goes to infinity, ln of x over x to the n equals 0. So all I'm trying to say here is that when it comes to how fast things are increasing, e to the x is generally a class of functions. These exponential functions tend to do this. They tend to go faster to infinity than anything else. The polynomials are kind of intermediary. And then the natural logs, the logarithm functions, go to infinity slowest of any of the major functions that we're dealing with. So keep that in mind. A lot of times this will be useful. This tells you that e to the x is increasing faster than p of x. That's what it means. That's very important in a lot of processes, noting when one piece goes at a different speed than another piece. Keep those in mind. Now, there was one last thing I wanted to do. It was a slight, I'll call it a semi-proof, because it's really not. There's a lot of assumptions in this proof, but the general idea is this. If I want to get the limit as x goes to a, f prime of x over g prime of x. And I'll tell you the assumptions that are being made as we're doing them. This is the limit as x goes to a f prime of x over limit as x goes to a g prime of x. This is, that's just a general rule of limits, so long as these limits both exist. That equals f prime of a all over g prime of a. So I'm assuming that f prime, g prime are continuous at a, and g prime of a does not equal 0. Well, I'll go to the definitions for the derivative at a number, and I'll get the limit as x goes to a, f of x minus f of a all over x minus a divided by, let me make this big, the limit as x goes to a, g of x minus g of a all over x minus a. These are from the definitions of the limits themselves. I'm just substituting those in. Then I'm going to go back a step and combine this into one limit. I'll have f of x minus f of a over x minus a times, I'll flip the bottom fraction, and then I can cancel the x minus a's. And finally, if I make the assumption that f of a and g of a are both 0, then this equals the limit as x goes to a, f of x over g of x. And this is making the assumption that f of a equals g of a equals 0. This is the gist of the proof. I don't want to do the whole thing because it's miserable. There's a lot of details that are just mind-numbingly difficult to keep track of. Like, I have to do this for all the different kinds of limits there are, first of all, so there's tons of cases. Second of all, there's like, you have to treat cases where g is 0 on an interval around the point and where it's not, so you have to separate that case, and I don't think any of that's very constructive for this course. So this is good enough. The trick, here's the trick that happened. We get to cancel these nice x minus a's, and that's essentially the game plan. Anyways, that's all I have for L'Hopital's rule. Next time we'll move on to a new topic.